Welcome to Math 150, Section 1, Lecture 13, 2021. This is multivariable calculus. And what we're going to be doing today is we're going to be doing Lagrange multipliers. So we've already talked a lot about the theory behind Lagrange multipliers and why they work. Now we're going to apply it to some specific problems. So when we do Lagrange multipliers, this is constrained optimization. Now, in an ideal world, I would give you an algorithm that gives you the answer. The quadratic formula is wonderful in that regard. You give me a, b, and c for my quadratic, I put it in, and it shoots out negative b plus or minus square root of b squared minus 4ac over 2a. That's the answers, we're done. Lagrange multipliers is not going to give you the answers to where the maximum and minima are. What is it going to give you? It's going to give you the... But is that the same as giving you the maximum and the minimum? Okay, but if it gives me the point, if I plug it in, I get the maximum and minimum. So it effectively gives me the maximum and minimum if it gives me them. Lagrange multipliers doesn't give you the maximum and minimum. What does it give you? Candidates. Okay, this gives you candidates. Then once you have the candidates, then you can check. And then you plug in, and hopefully one of them is clearly going to be the max, and one of them clearly is going to be the min. Or if certain problems, physically, you've got to be going for maximum or minimum. If I'm trying to find the point that's closest to a curve, well, if I go arbitrarily far on the curve, my distance is going to get arbitrarily large, so I should be returning a minimum. If I'm trying to find an area for a given perimeter, again, that should probably be a maximum, and I should know stuff like this before I start even doing any of the calculation. So a lot of times, you know what kind of points you're going to get. This should be a maximum, this should be a minimum based on just knowledge of the problem. What can you do? Well, sometimes we have second derivative tests or first derivative tests. And we can do this for interior points. For the points on the boundary, it's a little bit more interesting. And so the idea is you have, say, g of x1, xn equals 0. This is the constraint. Instead of equaling 0, it could equal some number c. So you should think of this as a level set. And then you have some function, f of x1 to xn. And then what you have is, at a candidate for the maximum or the minimum, you have the gradient of f at some point a is equal to lambda times the gradient of g at that point a, and g of a1 through an equals 0. Whenever you're doing math, you always want to try to do some quick calculations to see, do you have a hope for success? So if I have more equations than unknowns, in general, do you think this is a good thing or a bad thing to find a solution? A bad thing. So if I have two equations in one variable, I want 3x minus 5 equals 7 and 12x plus 11 equals 2010. It's unlikely I'm going to find something that satisfies both of them. So if I have more equations than unknowns, it's bad. What if I have fewer equations than unknowns? What do you think might happen if you have fewer equations than unknowns? I have 2x plus 5y equals 7. I have one equation but two unknowns. Do you think there's going to be a solution? So 2x plus 5y equals 7. Yeah. Do you think there'll be more than one solution? How many solutions do you expect? Infinite. In fact, you're going to have the equation of a line. So if I have fewer equations than unknowns, I might expect there to be infinitely many solutions. So the perfect balance, when we have just as many equations as unknowns, maybe we'll have only finitely many solutions in that case. And so the question is, how many equations do we have here? How many unknowns? So the unknowns, it could be a1 dot 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 an and lambda. So I have n plus 1 of these. And the equations df dx1 at a equals lambda df dg x1 at a all the way down to df dxn at a equals lambda dg dxn at a. And I still have my equation, my constraint g of a1 an equals 0. So I do have n plus 1 equations. So I have as many equations as unknowns. So I believe that there is a chance. Often we use x1, xn, and not a1 to an for the point. I felt like just writing a1 to an to just really highlight, here's my variables that I'm differentiating against, and here's the point where I'm evaluating it at. All right, so these are Lagrange multipliers. So we've talked about why this is true, that if I have some surface, and here's the normal to the surface, here's the gradient of g, if the gradient of f is not in the same direction as the gradient of g, then if I flow a little bit in this direction, I get larger. If I flow a little bit in the other direction, I get smaller. So the only chance I have, and here's maybe the gradient of g, and then if over here, the gradient of f is in the same direction, now if I move just a little bit, I'm not seeing any change in that. My instantaneous speed is 0. I now have a candidate. And really, we're going back down to Calc 1. If I have some curve on the surface, f of c of t, this is now a Calc 1 problem. But all we have to do is just remember these equations. How much calculus do we actually do for Lagrange multipliers? Where is the calculus?
Gradient.
Yeah, right here. This is the only place where calculus is. Everything else is algebra. Most of the problem is going to be algebra. Depending on what problem you look at, the algebra could be easy, it could be hard. Do we care about what the value of lambda is? No. What do we care about? What? I'm sorry?
We don't need the value of lambda, but we need to know this.
So what do we care about? What do we want to know at the end of the day? We want to know our candidate points. How do we find the candidate points? It might be finding lambda. But we might be doing some algebra and the lambdas might cancel and we might never explicitly solve for lambda. That's fine. At the end of the day, I only care about the point. If it helps you to find lambda, by all means, find lambda. But at the end of the day, the goal is answer the question that was asked. It's amazing how many times people do not answer the question that's asked. I'm trying to find where the function is largest or smallest on the constrained surface. Lambda might help, but at the end of the day, I don't really need it. But you sometimes have to be careful when you're doing the algebra and you have equations and you're dividing one equation by another. What is the greatest danger? If you're dividing one equation by another, what do you have to be careful about? The denominator being 0. So frequently what you will do is you will split things into separate cases. Case 1, the denominator is 0. All right, well, if the denominator is 0, then one of the sides of the equation is 0, and that's often not so bad to analyze. Case 2, the denominator is not 0, and I can go through and I can do the calculation. We could have the situation where the gradient of f happens to be 0. If the gradient of f happens to be 0, then it is a multiple of the direction of the gradient of g. What multiple would it be? So if the gradient of f is 0, what multiple of the gradient of g must it be? 0. So you have to be careful. You could have lambda equals 0. So when you're doing these calculations, just be very careful. Have you ever assumed anything? Have you ever assumed anything about one of the numbers? Whenever you see a division, always think, did I just divide by 0? All right, so the first problem we can do is Farmer Brown. All right, and what does Farmer Brown love? Be more specific. Everybody loves fences. I'm sorry? What kind of fences does Farmer Brown love? Rectangular, right? Farmer Brown would never consider a non-rectangular fence. So this is x, this is y. And my constraint is maybe g of xy equals 40. And this is 2x plus 2y, this is the perimeter. And the function f of xy is xy is the area. And I want to maximize the area subject to having 40 meters of fence. So we've already solved this. But let's solve this now using multivariable calculus. Now again, lots of different ways. I haven't written it as g of x equals 0. I could, of course, change it if I wanted to and write, g of x is 2x plus 2y minus 40. The reason it doesn't matter is at the very next step, I'm going to be taking the gradient of g, so whether or not I have this constant doesn't really matter. It will change how you do the algebra ever so slightly. It doesn't make any difference. Do people want to leave it as it equals 40, or do they want to have 2x plus 2y minus 40 equals 0? Or does it not matter and you don't care which way it goes? And you've already written this in your notes, so let's just do it this way. It doesn't really matter. And so this is all just which is the best way to do it. So let's calculate this. So the first is the gradient of g, which is dg dx dg dy. And that's going to be what's the gradient of g? 2, 2. Oh, this is great. And the gradient of f is df dx, df dy, and what's that going to be? I'm sorry? Y comma x. Do I first take the derivative with respect to x, so I just get y, and then I take the partial with respect to y and I just get x. So my equations are y equals 2 lambda, x equals 2 lambda, and then my equation 40 equals 2x plus 2y, so 2x plus 2y equals 40. I have 3 equations and 3 unknowns. There's lots of different ways to solve this. What's one way to solve it? Okay, why can I plug x into y? Yeah, they're both equal. So if x equals 2 lambda, which equals 2y, these tell us that x equals y. And if I know x equals y, I can then come into this equation and I get 4x equals 40, therefore x equals 10. Do we ever need to find lambda? I could take the ratio of these two equations and I could say y over x equals 1, therefore x equals y. What do I have to be careful about by doing that? If x is 0. So if x is 0, what does that mean about lambda? And if that's 0, what does that mean about y? And does 0, 0 satisfy the constraint? So case 1, x is not equal 0. We get x equals y, blah. Case 2, x equals 0. then we get lambda equals 0 equals y, not on constraint. So you just have to do a little bit more work in the second approach. If we try to say, hey, look, I've got 2 lambda and 2 lambda. If I just take the ratio, the lambdas cancel, and I get x equals y. But I have x in the denominator, so I have to be a little bit careful. We can deal with it. As a general rule, if I had to choose, I would much rather do a lot of easy problems than one hard problem. And so I'm happy to break things up into lots of different cases. And then I do each case, and I just make sure that each case is, that the union of all the cases covers every possibility. It's okay if some things are in multiple cases. I just want to make sure that everybody is covered. So if you are a first-year student, please raise your hand. Does that cover everybody in this classroom? If you're a first or a second-year student, raise your hand. Does that cover everybody now in the classroom? If you're an undergraduate, raise your hand. Does this cover everybody in the classroom? No. So if I just broke this classroom up into first year, second year, third year, fourth year students, I would not cover everybody. If I broke it up into first year students, undergraduate students, and people who have received an undergraduate degree as my 3 groups, that would cover everybody. And some people would be in multiple groups. Some people would be in both the first year group and the undergraduate group. That's fine. It's okay if your cases are not disjoint, but they must be exhaustive. They must cover everything. There's really only 2 possibilities for x. It's not 0 or it's 0. All right, any questions about this problem? Is it helpful to keep the Lagrange multiplier stuff on the board, or is this well enough understood now that that board space is not needed? Yes? Well, we know the gradient of f has to be lambda gradient of g, right? Gradient of f is lambda gradient of g. So y x equals lambda 2 comma 2. So y has to be 2 times lambda, and x has to be 2 times lambda. Okay. Do people want to keep this on the board? Or this can be erased? Can be erased? So again, there's not that much calculus. Now, there's a bunch of interesting problems that one can do. And I will admit that I'm much more looking forward to section 1 today than section 2. Because for some of the ones I haven't really thought about, it'll be fun to look at them for the first time with you. For section 2, it's hard to pretend to be surprised by what we see. So here was an interest. Well, let's start doing things in sequence. So let's look at triangles. So if I imagine I give you a right triangle, x, y, and z, and the perimeter is 1. What is the maximum area? Now, sometimes when you have problems, you can say, well, I might as well rescale things, and without loss of generality, I can assume the perimeter is 1. If the perimeter was 5, what could I rescale x, y, and z by? By 5. If the perimeter was 20, what could I rescale x, y, and z by? 20. I can always change units. So instead of measuring things in feet, I could measure things in yards. If I measure things in yards rather than feet, I rescale things by a factor of 1/3. If I measure things in centimeters rather than meters, I scale by a factor of 100. I can just rescale things. And as long as my number is not 0, I can rescale things to be 1. What I really care about is not the magnitude of x, y, and z, but the angle. Any of the 2 angles. Because once I know one of the angles, I know the other. What does your spider sense, what does your intuition tell you this triangle should be that maximizes. Now it just flipped at this point of the lecture. Oh, it's showing the screen. What does your intuition tell you should be the best triangle for maximum area? It's got to be a right triangle. What right triangle? Yeah, your intuition should be x and y are equal. And then, the question is, how would we prove that? Well, what's our constraint? G of x, y, z is x plus y plus z equals 1. And what's the function we're trying to maximize? So f of x, y, z is yx plus y over 2. X times y over 2. Or could I just maximize x times y? Am I maximizing the area if I do x times y? Technically, what am I maximizing? Double the area. If I maximize double the area, is that the same as maximizing the area? Why would I want to maximize double area? I'm sorry? It's easier. Why is it easier? Yeah, it gets rid of that factor of 1/2. And it's going to make the algebra a little bit nicer. Who is the patron saint of mathematics? Which New England transcendentalist? We've mentioned him once. Thoreau. And what was Thoreau's advice? Actually, it was simplify, which you can simplify to simplify, but it's more emphatic to do simplify. Before you start doing algebra, pause and think, what can I do to make my life easier? What can I do to minimize the algebra explosion that's going to be happening? And if there's things that I can do, let me do it. Frequently, you would never try to minimize the distance between two things. What would you try to minimize instead of the distance? Distance squared, because the distance involves a square root. If I can minimize the distance squared, that's the same as minimizing the distance. So maximum area, so we're going to maximize the double area. Okay, so we can try to figure this out. What is the gradient of G? I'm sorry? 1, 1, 1. What's the gradient of F? So let's see what happens. We now have, we want the gradient of F equal to lambda gradient of G. So we want yx0 equal lambda 1, 1, 1. So we get y equals lambda, x equals lambda, and 0 equals lambda. And of course, we have x plus y plus z equals 1. Is anybody worried? Okay, why are you worried? Don't you trust me? I mean, it's been a good chunk of the semester already. What's making you a little worried about this? Yeah, the 0. So if lambda equals 0, what does this mean about x? It means x is 0. And then what does this mean about y? Also 0. Huh. This is giving us something that's very problematic. What did we do wrong? It's really subtle the mistake we made. So if I give you a right triangle, can I choose x, y, and z freely? Why not? It has to satisfy Pythagoras. Z is not a free variable. Right? This is not the correct analysis. What would be the correct analysis? What should the constraint function be? I'm sorry? Well, I want to try to do it with one constraint. You can try to do problems with multiple constraints, but well, what do we know about z if it's a right triangle? I'm sorry? So z is the square root of x squared plus y squared. So I could say my constraint is g of x, y is x plus y plus square root x squared plus y squared equals 1. And f of x, y is the double derivative. Now I have the right set of constraints. So what do we need to calculate? Gradient of g and I. So one of them isn't so bad. Gradient of f is just going to be y comma x. Gradient of g is going to be a bit more involved. I take the partial with respect to x. What's the derivative of x with respect to x? 1. What's the derivative of y with respect to x? 0. Now I have the derivative of the square root of x squared plus y squared. And if you want, you can write this as x squared plus y squared to the 1/2. And so when I take the derivative of that with respect to 1/2, with respect to x, it's 1/2 x squared plus y squared to the negative 1/2. And then what's the derivative of x squared plus y squared with respect to x? 2x. And now we have to find the derivative with respect to y. We could do the calculation, or you could realize, hey, this function is symmetric in x and y. So if I just flip all the x's to y's, then that would give me the derivative with respect to y. And so a similar calculation will give me 1 plus 1/2 x squared plus y squared to the negative 1/2 qy. So we get y equals lambda times this, x equals lambda times that. So we're going to write things very carefully. Gradient of f is lambda gradient of g. So I get y is equal to lambda 1 plus the 2 cancels the 1/2, and we'll have x divided by square root of x squared plus y squared. And then we have x equals lambda 1 plus y over the square root of x squared plus y squared. And we still have the constraint equation x plus y plus x squared plus y squared to the 1/2 equals 1. Is there any more calculus to be done? It's all algebra. So you now have to look at the algebra and try to get a sense of how to attack it. again, for this problem, is the calculus hard? No, this is actually a fairly nice function to take the derivative of. Does this algebra look painful? I would say it looks painful. I have some thoughts as to how to do this, but it looks painful. Any ideas, any suggestions to help guide me? Okay, so how can I do that? Good. So one thing is I could immediately use the third equation to remove the square roots of x squared plus y squared down below. And I could say as x squared plus y squared to the 1/2 equals 1 minus x plus y. I can use that equation to simplify some of the stuff up above. And I get y equals lambda 1 plus x over 1 minus x plus y. And then x equals lambda of 1 plus y over 1 minus x plus y. And I'm writing it as quantity x plus y because I have an idea of what might be useful later. Any thoughts about what to try next?
Try to get rid of the fraction.
So how can we try to get rid of the fractions? What do you mean by multiply by the reciprocal? We multiply by. We have too many variables here. Is there a variable that we can get rid of? Okay, so what would how do we substitute for lambda? Sure. I mean, to some extent, something that would be similar. We just take the ratio, and if I take the ratio, the lambdas will cancel. The only concern I have is if I take the ratio, what happens if one of these expressions is 0? Well, if this lambda is 0, then x would be 0, and if lambda is 0, then y would be 0, and if x and y is 0, clearly that's not going to work. So we don't have to worry about lambda being 0. So we know lambda is not 0. Is it possible that one of these could be 0? How large can x plus y be? Can x plus y be as large as 1? The whole perimeter is 1. So we know x plus y is less than 1. So we know the denominator here is positive, so this is a positive number. So this expression here is positive. You can see how bad the problems become very quickly. But I know this has to be positive, so there's no way this number can be 0. So the only danger is if lambda is 0. But if lambda is 0, then x and y is 0, which is impossible. So case 1, lambda equals 0, that implies x equals y equals 0, which implies the perimeter equals 0, which can't happen. So case 2, lambda does not equal 0, and then if we take ratios, we get y over x equals 1 plus x over 1 minus x plus y over 1 plus y over 1 minus x plus y. Right? I'm just taking the ratio. The lambdas cancel. I have this over this. How would I add two fractions like this? Doing the same job. So I would multiply this by 1 minus x plus y over 1 minus x plus y. I have an x over here. I have a 1 minus x minus y. So when I add them, it's 1 minus y over 1 minus x minus y. Do you read that that's the numerator? When I multiply this by 1 minus x plus y, and I add that to this, the minus x cancels the plus x, and I'm just left with, oh, that should be, yeah, 1 minus y. And this should be a plus over here. And then when I do the other one, I'll get 1 minus x over 1 minus x plus y. Oh, that simplifies to 1 minus y over 1 minus x. So I get y over x is 1 minus y over 1 minus x. What can I do now? I want to solve this. What can I do? When do two fractions, when are they equal to each other? So when you look at this, what could you do that might make it a little bit easier to understand? I'm sorry? Yeah. Let's clear the denominators. And if I do that, look, it's going to be y times 1 minus x is x times 1 minus y. So y minus xy equals x minus xy. What can I do to both sides? Take out the xy and you get. So it's isosceles and a right triangle. Was the calculus difficult? No. Was the algebra difficult? Yes. So in setting up this problem, part one of setting it up is to recognize that we have a constrained optimization problem in getting the right constraint. Step 2 is to take the derivative. Step 3 is to do the damn algebra. Of the 3 steps, amazingly, the hardest step is the algebra from high school. The calculus is very straightforward. What is the best way to get good at doing problems like this? Doing a lot. If I really wanted you to become masters of Lagrange multipliers, I would give you a tremendous load of problems to do. I have no desire to have you reach that level of expertise. If you can do a problem like this, this is probably worse than any algebra that I would give you. On any exam, most of the points, or a good chunk of the points, would be just setting it up properly. To solve it, you need to be able to do the algebra. And you can start playing the different games and say, well, let me keep track of how many things I have. And if I have 3 equations and 3 unknowns, I should be able to work things through. When I have nice things like this, you always want to consider just taking the ratios because the lambdas will cancel. And okay, well, if I take the ratios, the lambda cancel, I just have to make sure I can do that. And the only danger is, what if I divide by 0? Well, if x is 0, then this expression is 0. So that means either lambda is 0 or this part over here is 0. And this part over here can't be 0 because I know this is 1 minus. Now you also see some of the advantage of starting off by saying the perimeter is 1. All right. There's a whole slew of problems we can do. And so one option, and I will let you vote, is I can do this problem again in section 2 because it's a great problem. Or I can do a different problem in section 2 so you would have another thing to look at. You want me to do? Okay, so what I'll do is I will now, so today there will actually be a real difference between the two classes. And again, this is one of the advantages is, we have the ability to just do lots and lots of practice problems. The next one I want to talk about is a nice one where if you look at it the right way, you can make things a lot easier. So this is problem number 37. They want you to look at a triangle inscribed in a circle, and they want it to have the maximum area. What's the radius of my circle? 1, right? You might as well assume the circle has radius 1. And so you want to look at all possible triangles and see which one has the maximum area. Now, depending on how you look at this problem, you can have a nightmare in terms of calculations to do. And so there's lots of different ways to do this. Without loss of generality, what can you tell me about some of the points? Okay, but I mean, I could write down the coordinates of each of these 3 points and then go through the calculation to find what is the area as a function of those coordinates. If I do it like that, it's going to be a monster. And I'm going to have lots of different constraints because they're all on the circle. What can you assume without loss of generality is true about one of the points? When we were doing our vectors, we often assumed one of our vectors was pointing in the direction of the North Pole. And we just assumed something like that. Where can you assume one of your points is? I'm sorry? But it's going to be on the unit circle. Where can we assume our point is on the unit circle? Well, 0, 0 would be the center of the circle. I need a point on the circle. Without loss of generality, I can assume my point is at. Give me a point on the unit circle. That's not on, that's the center. 1, 0. So if you want, one possibility is, let's assume that the first point is at 1, 0. And then we have to choose 2 other points. That's one way to do it. And now all of a sudden, I've cut down the number of parameters by 1. Or maybe even 2, depending on how many coordinates you have. Does that seem like a good idea? Yes. Try to do some simplification. This is Henry David Thoreau. Before we start doing all the painful stuff, can we simplify? There might be an even better way of doing it. I have 2 points here that determine the side. I can always assume that maybe 1, 0 is right between them. So rather than assuming it's like this, what if I assume here's 1, 0, and I assume that I choose my triangle oriented like that? Can I always do that? I'm given 2 points, I can just spin the circle so that the point right between them on the arc is at 1, 0. And now I have these 2 points located by just one angle theta. And this gives me one side of the triangle. Right? And now I just have to choose where my third point is. Correct? So I could choose my third point to be in through here or in through here. How do you find the area of a triangle? What's the formula for the area of a triangle? 1/2 base times height. So where do you think on this circle, if we consider this the base, where's my height going to be largest? Almost, either the leftmost point or. So all of a sudden, I'm now down to there's only 2 locations for the third point. Because if I choose my third point to be over here, then if I make this as my triangle, notice that the height is now only this much. The height is largest when it's over there. Unless these 2 points are on the other side of the center, in which case it would be over there. Do you see how by spending some time thinking about it, we have greatly reduced the problem? So now we basically have 2 cases. I have a triangle like this, and so the area is going to be related to just that angle theta. And so if the 2 points are closer to 1, 0 than to -1, 0, we should be able to do that. And now we have a triangle, so it's going to be so this is 1, this is 1, this is theta. And now we need to figure out what is the area of this triangle. So this line over here, this is also 1 unit. If this is theta, this is going to be the sine of theta, this is going to be the cosine of theta. Right? And so what's the area? It's going to be 1/2. The height is what? 1 plus cosine theta. And in the base is 2 sine theta. We've even eliminated doing Lagrange multipliers by analyzing this so carefully. I still have to do, what about it being over here? And so it should make sense that it's going to be on the other side that you're going to get the larger area. But by spending some time doing it like this, I've completely eliminated all the Lagrange multipliers. So depending on how well you can see the algebra, you can take a problem at various levels and really simplify it. And now at this point, how would we find the best value of theta? What would we do? So differentiate. So this is, say, f of theta. So f prime of theta, the 1/2 cancels with the 2. So this is just going to be sine theta plus sine theta cosine theta. And there's lots of ways to do the algebra here. So this is f prime of theta, derivative of sine is cosine theta, plus then the derivative of sine is, maybe it would have been better to just use the product rule. Derivative of sine is cosine, so we'll have cosine squared theta. And then we have sine times the derivative of cosine, which is minus sine. So we have a minus sine squared theta equals 0. So how would you solve cosine theta plus cosine squared theta minus sine squared theta equals 0? I'm sorry? So sine squared theta is the same as 1 minus cosine squared. Cosine squared plus sine squared is 1. So this is just 1 minus cosine squared theta. So we get cosine theta plus cosine squared theta minus 1 minus, so it's going to be plus 2 cosine squared theta minus 1. Okay? So I want to solve 2 cosine squared theta plus cosine theta minus 1 equals 0. Any idea how to solve that? Yes. What can I factor out? But cosine doesn't hit every term. Yeah, consider this as a quadratic. 2x squared plus x minus 1 equals 0. So cosine theta equals x equals negative b, which is negative 1, plus or minus the square root of b squared minus 4ac, which is going to be 9 plus 8 over 2. Over 2a, which is 4. Clearly, I don't want the negative because I don't want to have a negative sideline. So it's going to be negative 1 plus the square root of 9, which is, so it's negative 1 plus 3 over 4. So it's 2 over 4 or 1/2. Therefore, theta equals, so what angle has a cosine of 1/2? This is pi over 3 plus 60 degrees. So if this is 60 and this is 90, it should be 30, 30. This is 1 over here, this is 1 over here. If this is 60, this is 120. So this has to be 30, 30, 30, 30. What kind of triangle did we get? Equilateral triangle. The difficulty here is the algebra. And you're recognizing that when I have this, this is a quadratic equation in cosine theta. And I know how to use the quadratic formula. So I will do some more mechanical stuff, I think, in the second section. And this will give us lots of different Lagrange multipliers to see. The hardest part of these is to do the algebra. So on the exam, if you can set it up, that's worth a good chunk of the points. To get full credit, you would have to be able to solve. And you can see just what is required to actually solve. All right, so this is a good place to stop for the day.